In this class, we're going to be doing a lot of proofs. And we'll be talking about what is a proof, probably in lecture and through several modules. As I described in class, a proof starts with a mathematical statement that you'd like to prove. Now, sometimes this is referred to as a theorem or a claim. Sometimes it's a lemma, which is usually a statement that you prove in order to help you prove a more important statement, like a theorem. So, for example, we could write the following. Our claim is that the following Boolean formula x2 bar or x1 and x3 bar or x1 bar and x1 is satisfiable. So this is the claim that we would like to prove. So here's a mathematical statement. We'd like to prove that it is satisfiable. What is a proof? Well, it's a sequence of small steps that convinces us at the end that the statement is true. Now, what is a small step? Well, a small step is a step that is not too difficult to follow for someone who is reasonably competent in math or science. That's what my definition is going to be for this class. I might be able to write a proof, hopefully I'll be writing proofs that you understand that people with no mathematical experience have trouble following, but that's okay. I mean, proofs, simple steps should be steps that someone with a reasonable background in math, someone who did, say, OK in Calculus 1, should be able to follow. Okay, so for this claim, f equals this Boolean formula, and we want to prove that it's satisfiable. My first step to prove this to you is going to be to set x1 to be true. I'm going to set x2 to be true. I'm going to set x3 to be false. Okay? So this step I think is pretty easy to follow. We've just set these variables. Okay, now we'll see that the first clause, x2 bar or x1, simplifies to true because x1 is true and true or anything is true. So the first clause is true. I think that step was easy to follow. The next step is to look at this clause, x3 bar or x1 bar, and since x3 was set to false, x3 bar will be true, and true or anything is true. So the second clause is true. And the final step here, I'll write step 4, will be to look at this last clause with x1, but x1 was set to true, so the last clause is true. And then our final step will be to notice that, well, this clause is true, and this clause is true, and this clause is true. We just wrote that down. The first clause is true, the second clause is true, the last clause is true. Therefore, we can conclude that f is true. Given this assignment. Okay, so our conclusion is that f is satisfiable. Why? Because we gave an assignment to the variables that cause the formula to evaluate to true, and therefore we can conclude that f is indeed satisfiable. That was the claim that we wanted to prove, and every step, well, in my opinion, was easy to follow. So if someone asks you to prove something to them, and or you ask for a proof of something, and there's a step that you can't follow, you might not want to consider that a valid proof. Or if you think you have a proof of something and you're explaining it to one of your classmates and they can't follow one of your steps, then that might not be a valid proof because one particular step isn't simple enough to follow. Here's another example of a direct proof. So let's let f be the following polynomial. F of x equals a x squared plus bx. And I'm going to assume that a is a real number that's greater than 0. The claim is that minus b over a is a root of the polynomial f of x. Okay, so this is the statement I would like to prove. I'd like to prove that minus b over a is a root of f of x. Well, how do we prove that minus b over a is a root of f of x? Well, let's set z to be minus b over a, and I want to show that, so we need to show that a times z squared plus b times z equals 0. That's what it means for z to be a root of this polynomial. Okay. So here's step 2. What is z squared? Z squared equals b squared over a squared. And also a times z squared therefore equals b squared over a. Here's my next step. I'm going to look at b times z. That's going to be minus b squared over a. And then I'm going to just add up a times z squared plus b times z. And you can see that that is b squared over a minus b squared over a, which equals 0. And that's what we wanted to prove. Notice again, each step was relatively simple. I set z equal to b minus a. I squared it and multiplied by a. I multiplied b times z and I got minus b squared over a. And then I just added up a times z squared plus b times z. So I added b squared over a plus minus b squared over a, and I got 0. This proves that z, which equals minus b over a, is a root of this polynomial.